Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the course offered by Swayam Prabha at IIT Gandhinagar. This is a course on maritime structures under fire, blast and explosion, which is coordinated by me and Professor Gaurav. This particular course has got the contents of interest in the industrial perspective, and I am sure that you will be enjoying the contents of this course in the professional front as well. So in the last lecture, we discussed about the explosion characteristics. We will continue with that in the current lecture, lecture number 12, explosion series 4, where we will talk more details about the explosion characteristics. Okay friends, let us ask a question. How do we classify explosion? We already learnt it in the previous lecture, but just for our understanding, explosions can be classified in 5 basic types. You can classify them as vapor cloud explosion. We know when a large volume of flammable material, gas or liquid releases under pressure, it forms a vapor and that cloud when comes in contact with any heat or any fire source, it gets exploded. So, vapor cloud explosion is one serious concern of flammable materials. The second one which we saw in detail earlier was boiling liquid expanding vapor cloud explosion. So, when liquid being stored in a pressurized vessel come in contact with high amount of heat, they start vaporizing and the boiling liquid expands manifold, and when it is released it explodes. So, BLEVE is one of the very important medium of accident in many process industries. As we saw in the last lecture, BLEVE and VCE happened in UK and in Mexico, were classical cited examples of disaster accidents that could happen in process industries. In addition to that, we can also have pressure vessel explosion, condensed phase explosion and dust explosion. Friends, even dust can also explode. So, it depends upon on what condition the dust propagate and at what pressure they are handled. So, explosion classification comes under 5 basic types: VCE, vapor cloud, pressure vessel explosion, BLEVE, condensed phase explosion and dust explosion. We will see one by one in detail as we go forward. Let us talk about more on vapor cloud explosion. Vapor cloud explosion happens only under certain following conditions. Let us see what are those conditions at which VC can happen. You may wonder why we are talking about the conditions causing VCE. As a design for explosion resistant or explosion proof structures, we must always disable these kind of conditions as far as possible, so that the probability of VCE occurring in the industrial sector or on the work platform is minimum. So, to reduce the probability of occurrence of that kind of accidents, we must know under what conditions a vapor cloud explosion can happen. When you have a flammable material released at an appropriate temperature and pressure, this material can include liquefied gases under pressure, ordinary flammable liquids and gases, etc. When the flammable liquid spills, we know it vaporizes, and once it vaporizes, it forms a cloud. So, we call this as a vapor cloud. When this happens in large volume, the cloud disseminates in a large surface area and it occupies a large area which is now vulnerable to explode. So, if you have any source of ignition to ignite this vapor cloud, it becomes an explosive. So, ignition must be sufficiently delayed for a vapor cloud to form the maximum size. If the vapor cloud is the minimum originating size and ignited, it will vaporize and evaporate, it will not cause explosion. When the vapor cloud grows to the maximum cloud size and when comes in contact with ignition, it becomes an explosion. So, vapor cloud explosion needs a lot of open area to form, and we must avoid leakage of any flammable material which can vaporize faster. If the ignition occurs instantaneously at that time, it will also cause something called as a fireball, which we already learned. Fireball is actually a spherical form of fire which propagates with a high velocity and speed. For VCE to form, there is a specific fuel air ratio. If the fuel air ratio is not sufficient enough, vapor cloud may not form. So, other way of controlling or decreasing the probability of occurrence of vapor cloud explosion is change this fuel air mixture. So, bring this mixture out of the flammable range. If you are able to bring it out of this range, then it may not cause explosion at all. So, in the later part of the lecture, slowly we will discuss about the flammability diagrams. There we will see how flammable ranges can be altered for a given fuel air mixture. A uniform fuel air mixture closer to the stoichiometric fuel air ratio will cause a very strong explosion, that is important. So, therefore, friends, it is necessary to understand the VCE formation. We must know what is the fuel air mixture, and what is its stoichiometric fuel air ratio? If the stoichiometric ratio is very close to the fuel air mixture, then the explosion is going to be disastrous, going to be very strong intensity. So, there are two conditions where VC can be avoided. Let us see what are these conditions. Condition number 1 could be VC can be avoided if the fuel air mixture can be handled away from the flammability range. Then one may ask me a question, how do we know the flammability range for a given mixture? Friends, for every mixture there are two ranges within which it can catch fire. One is called the upper flammability limit, the other one is called the lower flammability limit. We call this as LFL and UFL. This is UFL and this is LFL. Okay. If I am able to take the fuel air mixture ratio away from this and away from this, then it will not catch fire at all. So, flammability diagrams are very useful in controlling explosions. To control actually fire, and I will not see much difference between fire and explosion because it is only a process difference. So, nowadays friends, all industrial plants, sectors in maritime industry has AI driven flammability control mechanisms. So, we will talk about this later when we understand how to draw a flammability diagram and how to use it for avoiding explosions. So, now we have got artificial intelligence coming into play in controlling the flammability mechanisms occurring in the process plants. So, as we saw friends, if the fuel air mixture is not in the range closer to the stoichiometric ratio of the mixture, then explosion cannot happen. So, that is the first condition we have. The second condition we have is that it should not be instantaneously available. Ignition should not be instantaneous. On the other hand, you should avoid large vapor cloud formation. If vapor cloud formation is restricted, then I can always control the explosion process, that is for VC. Moving forward, let us talk about what is pressure vessel explosion. Pressure vessel, as the name suggests, occurs under certain combinations. Deflagration and detonations of pure gases which are not mixed with oxidants are classical examples of PVE. Example could be acetylene. It is a pure gas, has no mixture of air, so it can either deflagrate or detonate. Combustion deflagrations and detonations in the enclosure under high pressure in the enclosure, it can also result in pressure vessel explosion. The explosives could be in different states, can be even gas or liquid or even fine dust particle fuels, can say spray gas okay, gasolines can also be sprayed, can be fine particle fuels. If you have that kind of fine particle fuels, can also cause pressure vessel explosion, provided they are kept under pressure in an enclosure. If an enclosure is too weak to sustain the pressure resulting from this expansion or combustion process, it will crack and leak, and that will cause an explosion. So, friends, to reduce the probability of occurrence of PVV, what factors do we control? One, we must control and we must inspect the pressure vessels, for no cracks, no leaks, and the pressure inside is less than the allowable or admissible pressure of the vessel. So, this can be easily monitored. You can always keep a pressure sensor or a pressure gauge which can have continuous recording, and if the recording of pressure exceeds maybe even 75% of the capacity of the vessel, we can generate an alarm system. So, then the pressure release valves will operate and the pressure can be controlled. So, one can reduce input impact on the pressure vessels by inspecting them regularly and taking care of these ideas. The second place where this can happen is, one should not allow the presence of gas, liquid and dust particles in any enclosed surface. In any enclosed surface, this should not be available freely, because this will again result in explosion. Okay. So, now let us move forward and see how a PVV can react to form an explosion. Pressure vessel explosion is an exothermal chemical reaction which can cause an accelerated condition if there is any delay in the process of removing the released energy. The released energy caused because of excessive pressure in a container should be released instantaneously using what is called pressure relief valve or pressure relief mechanisms. If you delay that process of release of this excessive pressure, it can cause PVE. If the pressure in the containment vessel exceeds the pressure capability of the vessel, as I said, it can explode. And overpressure of the equipment with non-reactive gases can also result in PVE, but termed as mechanical explosions. When two streams of mixture with a widely different temperature occur suddenly, can also cause PVE. This is a very common example in paint industries. Even in chemical admixtures industries, this is a very common case. You have two different stream or set of mixtures operating at widely different temperature. One will be in a colder part, other will be in the hotter part. If you have these two come across together, then it can also result in pressure vessel explosion. It can cause flashing of the cooler liquid to generate vapor and develops pressure. If this developed pressure exceeds the capacity, it results in PV. Okay. So, friends, we have understood how the probability of vapor cloud explosion and pressure vessel explosion can be reduced. What are the possible factors which contribute to the VCE and PVE? In the design perspective, we have learned that flammability diagrams are very useful in controlling or reducing the probability of VCE. So, we must have to tune the air fuel mixture ratio to lie away from the lower and upper flammable limits of this mixture, so that this mixture cannot catch fire or cannot explode. Having said this, let us move on to the third category or classification of explosion, which is more vulnerable in process industries, especially in maritime sector of oil and gas processing plant, LNG storage plant, LNG processing plants, CNG plants, etc., which is boiling liquid expanding vapor explosion. So, you would have learnt a few topics of this in advance earlier in the previous lectures. BLEVE is a special form of pressure vessel explosion. Okay, it is a special form. It occurs when large amount of pressurized liquid is suddenly released into atmosphere. One can ask a question, how from a container vessel large amount of pressurized liquid can get released? That is a good question. So, it gets released when the vessel fractures, that is one, or when there is a leak in the connections. Sometimes because of the corrosion on the vessel plates, vessel material degrades, and that can also cause leak. Sometimes you would see in many boilers there will be surface wetness. This is actually a micro pore which is allowing the liquid content to evaporate through these pores, and that happened because of the vessel degradation, material degradation due to corrosion. And we know hydrocarbons are highly corrosive, therefore, this is quite possible in all pipelines. BLEVE may also cause a huge billowing effect, and it can result in fireballs. Let us ask a question, what is the primary cause of a BLEVE? Primary cause is impingement of an external flame on the vessel. If a vessel under external pressure which is containing flammable liquid or gas under high pressure, if it comes in contact with an external flame, then the vessel ruptures. When it ruptures, the liquid level or the liquid expands manifold, and that causes explosion. It weakens the container and causes explosion. So, sometimes people also call this as blast. Okay. So, this is actually not a blast, it is an explosion. Blast and explosion are different phenomena, but people mistakenly call this also as a blast. So, BLEVE also occurs when sealed container of liquid gas is accidentally exposed and engulfed in fire. This is a very common example where the bottling plants, LNG plants, catches fire. There have been accidents, read in newspapers, you would have read, the LNG bottling plants caught fire. The LNG cylinders may be really empty, but a small amount of gas present in that, when released accidentally from a sealed container, can also cause explosion. Vapor under this condition is generated, causing a rapid rise in internal pressure. As a result, the container wall temperature rises and weakens its strength. Therefore, friends, even in the pressure relief valves, even if we have them in the vessel, stress imparted by this pressure is much higher than the capacity of this valve or the valve strength. The valve may be intact, but the valve strength is degraded and the valve ruptures, and that releases superheating liquid, and that causes BLEVE. The released superheated liquid expands manifold and vaporizes within a very short time. So, milliseconds it vaporizes, causing a catastrophic damage, spreading the ignited vapor for a very large surface area. Okay. So, the serious consequence of Blevy or you can say consequences. One, it spreads the vapor cloud over large area. Two, it spreads the cloud much faster, and when the cloud gets ignited, it results in explosion. So, the whole cloud turns into fire. So, it is a very catastrophic accident. Blevy accidents cannot be controlled, that is very important. Blevy accidents cannot be controlled with conventional firefighting equipments, and personal protection equipments under Blevy will not suffice. So, there are many fatal accidents happen and many people die when Blevy occurs. So, essentially the fundamental problem which is causing Blevy, the fundamental problem causing Blevy is expansion of pressurized flammable material. The flammable material can be gas, can be liquid, can be even dust, fine dust also, right. So, that is what we are trying to tell. Now, let us see the flow chart of Blevy. How does it look like? If a pressure vessel contains gas or liquid, if it develops over pressure, then it has got a possibility of Blevy when there is an ignition source. When the overpressure development occurs and when the overpressure development is in contact with the ignition, then there is a possibility of Blevy. If the ignition is delayed, it will result in vapor cloud explosion or what we call as flash fire. If it is immediate, it causes a fireball. So, all these are secondary consequences of Blevy. If you have no ignition source and if the material is non-flammable, no worry, it will not catch fire, no explosion occurs. But it is not true in the case of maritime sector, because when you talk about oil and gas production platforms, processing platforms, even port and harbors stocking LNG containers, we have highly flammable liquids present in the containers or on the platforms. So, they are very highly flammable, and source of ignition can always happen because of mechanical fault, electric short circuit, or even heat working conditions like welding, grinding, etc. So, these are all inevitable in any heavy industry. So, there is always a high probability of the presence of these factors which can cause Blevy. Okay. So, Blevy can cause a major accident. Overpressure and ejection of vessel fragments are common consequences of such explosions. Blevy also generally follows a fireball if the substance is flammable. When a vessel undergoes a Blevy, part of the released mechanical energy is converted into overpressure. There are different methodologies to calculate this mechanical energy based on diverse thermodynamic assumptions. The few models are listed on the screen: constant volume energy addition, real gas behavior and isentropic expansion, isothermal expansion, thermodynamic availability, ideal gas behavior, real gas behavior and adiabatic irreversible expansions. Different researchers have suggested different models in the literature which can help us to understand the thermodynamic basics of Blevy process. Having said this, let us expand our learning of Blevy slightly more in detail. Under exposure to fire below the liquid level in the pressure vessel, heat of vaporization of the liquid develops a heat sink, which is similar to a tea kettle. Friends, it is very important, under exposure to fire even below the liquid level, you do not need any external source of firing at all. This will develop a heat sink by itself. Under normal conditions, the evolved vapor will exist through the relief wall, but in case of flames impinging on the vessel above the liquid level, walls of the vessels are weakened, causing rupture of the vessel. Therefore, even if relief valve is opened, it will not help much. The superheat now available or created provides explosive energy for Blevy, which is maximum at superheat temperature. Blevy can therefore occur only due to mechanisms that cause sudden rupture or failure. That is very important aspect here. Friends, if you have a mechanism which is causing sudden rupture or failure of the vessel, then only Blevy can occur. So, as a designer, under explosion, we must try to show and prove and check that the containers do not rupture at any worst temperature and flammable quantity available in the container, and the connections are intact, which is ensured by regular inspections and safety audits. A sudden rupture therefore normally occurs under impact of sharp objects. So, we should avoid drop objects problems, suspending vessels in a high altitude or level where accessibility is very limited, non-inspecting metal surface which could have already corroded, and vessels could have manufacturing defects or internal overheating. So, this has got to be checked very thoroughly in periodic inspection safety audits, so that they do not have any issues which can result in Blevy. So, let me remove these parts and let us mark the important aspect which are causes for Blevy. Let us mark them. Let us say Blevy can occur when the vessel can suddenly rupture, the vessel can fail beyond its capacity, whether the vessel is subtender or subjected to any sharp object impact, whether the material degradation happened because of corrosion, and the vessel has got manufacturing defects or internal overheating problems. So, these are all a mechanical engineer's purview, where one can always control this, so that Blevy accidents can be very well controlled in maritime sector. Having said this, friends, accidents caused by Blevy have very serious consequences. We have already seen an example of Mexico accident, where Blevy explosion of a storage tank took place. This tank contained LPG of about 12,000 cubic meter and is one of the largest LPG tank supply to the city. The explosion caused more than 500 deaths, about 5,000 people injured. This is referred as one of the deadliest industrial explosions occurred in the world. The gas leak initiated the disaster, likely caused by a pipe rupture during the transfer operations. The plume of LPG was concentrated at ground level at about 12 minutes, which could have been contained and controlled, but later it grew much larger and was drifted towards the windward side. The explosion shock wave destroyed dwelling units located even up to 7-kilometer range. That is the devastating effect of this Blevy accident happened in Mexico City. Even dwelling units located range of about 7 km circumference were all damaged severely. Window glass panes broken, houses were damaged. There were damages notified even at 10-km interval distances from the Blevy source. The radiant heat generated by the inferno incinerated most corpses to ashes, with only 2% of recovered remains left in the recognizable condition. That is a very saddest part of this. Out of so many people died, even the face, even the body, nothing can be recognized. They all become into ashes, because this is occurring at a very high temperature. It completely destroys and destructs the target source. So, BLEVs are very unfavorable and unpreferred. Even their accidents, they should be completely avoided by all means, by design, by material choice, by operational status, by safety audits and periodic inspection and maintenance. Blast effects from BLEV are insignificant but important in near field design. One of the serious consequences is a large quantity of TNT will be released. Then the question comes, what is TNT? We will talk about this. One of the equivalents of explosion which is used in oil and gas industries. The blast wave thus produced depends on few factors: the type of the fluid released, energy during the release, rate of release, shape and size of the vessel and type of the rupture. We will do a couple of example problems to compute the BLEV accident later in the next lecture. BLEV effects consider the rapid expansion of the liquid and expansion of compressed vapor present in the head space of the pressure vessel. The explosion energy of BLEV can be given by this equation, where E is the explosion energy, V is the volume of the vessel under consideration, and P1, P2 are the initial and final pressures available in the operational sector. Using the analogy of maximum potential work done by the compressive gas, batch energy released using BLEV can also be computed using this equation, where the subscript 0 refers to a dead state, which is ambient condition, usually is 298 kelvins, 101.3 kilopascal pressure. E is the batch energy in kilojoules per kg, and U refers to internal energy, P refers to absolute pressure, and V refers to the specific volume, and T refers to absolute temperature, where S is the entropy. So, one can use equation 2 or equation 1 to compute the energy explosion release during a BLEV. Once this energy release is computed, how to compute the damage caused by BLEV, we will see in the next example in the next lecture. So, friends, let us look at the summary of this lecture. In this lecture, we learnt about vapor cloud explosion, pressure vessel explosion. We also learned something about fireball formulation. Then we learned more in detail about BLEV. For all these classifications of explosion, we learned what are the factors responsible for such explosions, how to reduce the probability of occurrence of such explosions, and what could be the design factors that can contribute to reduce the consequence of these explosions. We also learned how to compute the energy released during BLEV. So, in the later lecture, we will discuss an example problem to understand how this can be computed for a real time scenario. Hope you have followed the lecture. We are on lecture 12 on the course of maritime structures under fire, blast and explosion, and I believe that this lecture 12, including the previous ones, have educated you more towards preparing a basics of understanding fire, explosion and blast before we look into the design aspects as recommended by the code. for fire, explosion and blast loads. Thank you very much. Namaste.